Okay. In this problem, we're doing what's called using an integrated rate law for a first order reaction. So these are the integrated rate laws for section 3. At a certain temperature, the rate of this reaction is first order in H3PO4, that's phosphoric acid, with a rate constant of 1.10 reciprocal seconds, 1/seconds. The balanced equation is given. 2H3PO4 dissolved in water forms P2O5, also dissolved in water, plus 3H2O, also dissolved in water. Suppose a vessel contains H3PO4 at a concentration of 1.34 molar. Calculate the concentration of H3PO4 in the vessel 0.840 seconds later. You may assume that no other reaction is important and round your answer to significant digits, okay? So for this particular problem, notice what you're given. You're given the value of the rate constant with the units, 1.10, right? You're also given the balanced equation. And then you're given what we're going to call this the initial concentration. Suppose a vessel contains H3PO4 at a concentration of 1.34. That means we're starting with a concentration of 1.34 molar. Calculate the concentration of H3PO4 later in time, 0.840 seconds later. Assume no other reaction is important, okay? So this is an integrated rate law problem in that you're given an initial concentration, you're asked to find a final concentration or a concentration later, given the rate constant. So I'm going to go through this problem as an integrated rate law problem. And first you want to recognize that it is an integrated rate law problem, because anytime you're given a problem where they give you a concentration and then they want you to find the concentration later in time, that would be an integrated rate law. Likewise, if they said, how long would it take for it to get to some value, that would be an integrated rate law problem. The simpler ones are the half-life problems where it's a multiple of the half-life. But if you're not doing a multiple of the half-life, then we're going to use this approach that we're going to use here. So first of all, note that it's first order. They tell you that twice. They also give you the units of the rate constant. The units of the rate constant also tell you it's first order. Okay. So let's bring this up. I'll bring up the whiteboard and we can take a look at this problem. And just bring up. Okay. So H3PO4, I'm not going to put the states of matter, is going to give you P2O5 plus H2O. Okay. Now, the balanced equation, there's a 2 and then a 3 on the water. We know it's first order, so that means the rate is equal to the rate constant times the concentration of H3PO4 to the first power. So I won't write an exponent. So be careful. Don't write a 2 there. Don't write a 2 as in the exponent, because there's a 2 as a coefficient. You have to read the question. It tells you it's first order. So that means the exponent's a 1, right? You can put a 1 there. Most people don't do it, but that's fine. If it's first order, then there's several equations you can choose from. Integrated I, rate R, laws, IRLs. If it's first order, one form of the equation you can use, I'm going to use the symbol A for the reactant. Okay, so A is the reactant. So for us, it's H3PO4, but we don't need to write out the formula H3PO4 each time. We'll just write A. Okay, it's a math problem. So this can be rearranged as ln A minus ln A naught equals minus KT. Okay, that's a different way to write it. So let me point out some pieces of information. We know what K is. 1.10 reciprocal seconds. We also know that the time is 0.840 seconds. And we know that the initial concentration of H3PO4, remember the little 0 sign means initial, so that's the initial. And I'm just writing A0. I'm not using the bracket notation. I'm not writing H3PO4. A is the reactant, in this case H3PO4. The 0 means initial. Okay. And that initial concentration is 1.34 molar. Okay. So really what this comes down to is just an algebra problem. We know what T is, 0.840. We know what K is, 1.10. We know the initial concentration is 1.34. But what we're asked to determine is the concentration of H3PO4 after the 0.840 seconds. So that's another way of saying we just want to find out what A is. Okay? So I'm going to write that equation down here again. And notice I went with this form of the equation. And the reason I didn't go with the first form. The first form, the A and the A0 are in the parentheses together. We want to find just A. So you want to have it separated from the A0 so that you can isolate A all by itself. So the second form of the equation does that. It has them as separate. Okay. I'll show you how to get rid of the ln. So now if we want to find A, let's add ln A0 to both sides. And so when that becomes 0, right? So now you just have ln A equals minus KT plus ln A0. Again, if you want to write in H3PO4 with the brackets, that's perfectly fine. Now I'm just going to substitute in all the numbers. So ln of A is minus K is 1.10 reciprocal seconds. T is 0.840. And then plus ln of 1.34. Okay. So those are their three values. See how I put them all together? I put all the numbers together. That's a nice little technique you can use for organizing these problems. Put all the data in one little table. That way you can refer to it quickly. Okay. So now I'm just going to put everything in the calculator. And we're going to get ln of A equals 1.1 times 0.84 is 0.924. So it's negative 0.924. Reciprocal seconds is 1 over seconds times seconds. So there's no units there. Plus ln of 1.34. The ln button, you're going to use the ln, not log, unless you have a special calculator. Ln is the natural log. Now, very often you have to type in, push the ln, type the number in, put equal sign. Some calculators, you type the number, then you hit ln, and it does it. You don't have to hit the equal sign, but you have to determine which kind of calculator you're using. So I get 0.2927, so 0.2927. That's what happens when I take the natural log of 1.34. I'm going to add those two numbers together. Notice you're adding a negative and a positive, and the negative is a larger value than the positive, so you'll get a negative answer. So I get negative 0.6313. Now, how do we get rid of the ln, right? Because this is ln of A. We don't want ln of A. We want A. Okay, so here's what you do. I'm going to circle this just because we'll come back to it. If you have ln of x, let's say ln of x equals, some number. I'm just going to write a number. I could use a variable, but I'll just use like 3. What you do is you use the inverse of the natural log, and that's the exponential. So you use the exponential of ln of x. And what the exponential does is it gets rid of the ln. They counteract each other. Okay? But whatever you do on the left side, you got to do the same thing on the right side. So e to the 3. exp. So some calculators, it's e to the x. Some calculators, it's exp. Some calculator, I guess it's usually either ex. It's probably most likely e to the x. Most of the calculators do that. So the reason that this works is that now you're just going to have exp to 3. That's just going to give you a number. So you'll get a number over on this side, and then the EX, this is not canceling like 2 divided by 2 is a cancellation. Really what these are doing is they're undoing each other. So it's like if you took the square root of something and then you squared it, the squaring undoes the square root. You're doing the same thing here. The EXP undoes the LN. And then that just leaves you with X. So X is now going to be a number. Okay. So E to the ln of A is equal to E to the minus 0.6313. Now notice I just wrote E. I didn't write EXP. On your calculator, you're using EXP or E to the X. But we usually just write it as E. E raised to a power. That will get rid of the ln. So now you'll just have A on the left side. Practice with it. That's going to be E to the minus 0.6313. That comes out to 0.5319. 2 significant digits would be about 0.53. And that would be your answer. Oops, sorry. 0.53. Okay, so it went down. Now, if you think about it, it should go down, right? It's a reactant, so it should decrease. So after some period of time, it should go down by some value. So it did. It went from 1.34 down to 0.53. Okay, so there's your first law, integrated rate law type problem. Pretty standard. Some of the problems they'll ask you to, find the time, but they'll give you both concentrations. In this particular example, they give you the rate constant, they give you the time, they give you the initial concentration, and then they ask you for the final concentration. Okay, take care.